Okay, we're looking at Chapter 1, Ingredients of Change, Functions and Limits, and this is Section 1.8, Logarithmic Functions and Models. So let's look at a logarithmic model. So for algebraically, a logarithmic model has an equation in the form f of x equals a plus b ln of x, where a and b cannot equal 0 and they're constants, and x has to be greater than 0. Now note, when you have f of x equals ln of x, we have an intercept at 1, 0. Now, when we have a in here added in, what happens is the new intercept is actually going to be of the form 1 comma a. All right, and so that helps us kind of look at things as, transformations and stuff. The b also has an effect, but the key thing is our intercept here. Now, verbally, a log function has a vertical asymptote at x equals 0 because it's never going to be equal to 0 on there. Okay, so it's a vertical asymptote, and it continues to grow or decline as x increases without bounds. So as you see, as we get closer on this one to 0, it's climbing, but as we get closer to 0 here, we're declining and we're getting closer to negative infinity. And the graph of a log model has the form of one of the two graphs here shown in figure 1.82 and 1.83. Now the sign of b, in this case, b less than 0, and here we have b greater than 0. Uh, Less than 0, we have decreasing. Greater than 0, we have increasing. And greater than 0 is concave down, and less than 0 is concave up. And so those are kind of some of the key things about the logarithmic graphs. So let's look at these and see if we can determine what model fits each of these graphs. So first we have to identify each graph as either increasing or decreasing, then identify the type of concavity for each graph, and then match each graph with its equation. All right, well, what do we have here? Well, this one, that's going down, so that's a decreasing. And its concavity, well, it's concave up. And so now let's do this one. Well, this one starts down here and from going to x increases without bound, it goes to increasing. And that means it's concave down. Now this one is going up, and this one also is going up. So both of these are increasing and concave down. Now, if we look at just the b's now, all right, here we have a +2, so that means it's going to be greater than 0, so it's increasing. This one's a -2, so that's decreasing. Well, that one, that's right there. We've got that one. So this one has to be, if we call that A, B, C, and D, this one has to be B. Okay. Now, another thing we can look at is if we look at our A over here, all these are positive, but this one, we have a negative. Well, that negative means it's going to be 1 comma negative 1.4 as the intercept. And if we go and look here, that's where that where it should be at, is at the intercept down here. And so this part is going to be where it's intercepting. Okay, and so that point on the graph then is going to be this one. So that means this one is D. Now, we know that this is increasing concave down, and so basically, what's left over in those two, that's going to be A, and this one has to be then C. So those key points kind of help us get one of them, and then the other one we can find with elimination. Now, what is the end behavior? So there's no starting value such as f0 because we know that f0, there's that vertical asymptote. And so the log function is also defined for only positive input values. So it has to be greater than 0, okay? And so if we look at the increasing log function here on the left, the function is concave down. The b is going to be greater than 0. Now, as we get closer to 0 from the right, which means coming in this direction, what happens? Well, it goes to negative infinity. And as we go x out here, go that direction, what happens on increasing function? Well, it just keeps going up to positive infinity for the end behavior. Now, the decreasing log functions, what happens there? Well, the function's decreasing over the course of as we increase with x. And as we do that, that b has to be less than 0, and therefore it makes it concave up. Now, the limit as we get closer to 0 from the right, it's going to go up, 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 and keep going to positive infinity. Yet, when we go out here and go out to the right, what happens is it goes down to negative infinity, okay? So let's look at an example here. So it says the table below and the figure on page 82, which happens to be right here, gives a total amount of outstanding consumer credit between 2000 and 2008, excluding loans secured by real estate. What type of concavity is suggested by this scatter plot? Well, if we look here, it looks like it's going up like that. So concavity would be down, concave down. Now, what does the end behavior suggest by the scatter plot as the input increases? Well, it looks like as we keep going higher and higher, this keeps going up and up. So what the end behavior suggests on this one is, let's call this limit, and we don't know what the function is, so we'll call it f of x as x goes to infinity is equal to infinity. And when we go this way, what happens is it looks like it's continuing to go down this way. And so the limit of f of x as x approaches 0 from the right is going to go to negative infinity, okay? So that's kind of our two end behaviors for this graph. We have one going one direction and one going the other direction. Now, really, what does it matter? This is the end behavior we're talking about, really, is going this way. So this one is kind of a given, it's going to the 0, but this is the key one that we really need to know there, okay? Now, does the output appear to increase faster for smaller input values or for larger input values? So basically, where's the bigger jump as we move from left to right? Well, if we look here from left to right as we go this way, well, there's a pretty big jump here, but then it gets smaller and smaller and smaller, and it looks like it decreases as it go up. So the output appears to increase faster for smaller input values than larger ones. So I'm just going to circle the smaller input values because over here on this side, there's bigger jumps. Now we're supposed to find a log model for the data. So what we need to do is we need to go into our calculator and we need to type the data in. So we go to our stat plot, we edit, and I've already typed the data in to save time. And so what we have is their data is right here. And we're supposed to find a log plot. So we go back over here to stat, we go over to calc, and now we're doing the ln regression. So we number 9. And we have L1 in the X, L2 in a Y. So we enter, 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 and we get this as our value. So now let me do this. I just learned about this. Let's copy that. Let's go back to here. Now let's paste it if I can. Does it let me paste it? Oh, it might not let me paste it here. Okay, well, that's why it doesn't help me. Okay, anyway, so what we need to do is we need to write our function down. And so this is consumer credit based on Y. So let's call it C of Y is equal to, now we have negative 1585.229, and then it was a plus 1435.942, and then 942, and then ln of y, and that was in billions of dollars. And we need to say that then y is years since 1990, and y is going to be less than or equal to 18, but greater than or equal to 10. Okay, and so then that would be our model for part D. All right, so I'll stop at that and then I'll come back in a little bit.